All right, now let's use MATLAB to explore Taylor series. Now we're going to do this in two steps. The first is we'll develop the Taylor series using the symbolic processor, and the second is that we'll use numerical functions to evaluate it and plot it. So to start, I'm going to declare x and y as symbolic variables. Okay, and you can see them over here. Symbolic variable actually shows up as a 1 by 1 matrix. That's what that 1 by 1 means. And let's say that y equals sine x. Okay, so there we've got it. Now, Taylor series are pretty straightforward to type in. I'm going to say Taylor and y. The variable is x, and I can just hit return now. And there it is, up to 5th order. Now, what happens if I want it to a higher order? Well, it's easy enough to do. Type in the keyword order, and then just tell it what order you want. Say 11. Now, there's a quirk here. You can see that the Taylor series has 1st, 3rd, 5th, 7th, 9th order. And the reason is that some of the terms are 0. Basically, the even-powered terms are 0. They exist, but coefficient for those orders is 0, so only the odd number orders remain. Now, I asked for 11, and it only gave me 9. Watch this. If I go to 12, I now get the 11th power. I think what it's doing is it's counting the x to the 0 power as one of the terms. Now, one thing to notice here is how the denominators get just enormous quickly. Well, this is how factorials behave. So you can see 6, 120, 5040. What's that? That denominator is so big that unless x is large, that term is going to be very, very small. Okay, so I've got a Taylor series up to the 11th power, and one thing to note is that I've expanded it about 0. That's the default. Now I can expand this about other points if I want. Let's get rid of that. Let's go down from 12th order. What I can do now is delete some of this. I'm going to let it default to 5th order. When you type in the command, the first variable is the dependent variable, the second one is the independent variable, and the third one is the point about which you want to expand. Well, let's just say pi. Pi is programmed into MATLAB. It's 3.14159, whatever. So let's do this. Now I've got a different series, and it's expanded about pi rather than a equals 0. So let's going to clear that out, or clear the command window. Let's go ahead and say T11 equals Taylor y x. I'm going to let it expand about 0. So this is really a MacLaurin series. And let's make the order 12. All right, so there's that expression. Now let's start plotting this, but let's also make Taylor series expansions for lower order approximations. There's a couple ways I could do this. I could execute that Taylor command a couple more times, but I'm going to want to plot this, and I'm going to want to maybe do some calculations, and I can't do that symbolically. So how are we going to do this? Well, how about this? I'm going to clear the workspace. Now, this is a little dangerous. Now, the only place this result exists is on the screen. It only exists in text. It doesn't exist in the workspace anymore. So what I can say now is there's no variable T11 now. That variable doesn't exist anymore because I cleared the workspace. I'm going to make a numerical variable, and I'm just going to call it this. I have that text. Let's copy it and paste it right there. Now, that variable exists as that function exists as an anonymous function in memory, or in the workspace. Well, what would it look like if I had the 9th power? Well, let's do this. I don't need that term anymore. So now I've got 9. What about 7? Well, let's just keep doing this. There's 7. Well, little's good, more must be better. let's do it this way. Let's recall that. Let's make that 5. And let's just keep. And there. Well, I guess I could do T1. It's just X. Well, now I've got all of these. What am I going to do with them? Well, I might as well make some plots and see what happens here. I'm going to need the exact function. So let's just say T underscore EX for exact. We'll just call that sine X. So with all that loaded into the workspace, let's start making some plots. So let's say T exact. And let's go from minus 2 pi to 2 times pi. There we go. And I'll probably want to turn the grid on. So what's that look like? Yeah, pretty good. Pretty good. Now, this is my exact. I'm going to want to make real sure I can see it. And I also want the axis limits to be a little higher than that. So to start, I'm going to click there, double click, and go to the property inspector. I'm going to make this number 1 bright blue, and I want to make it big so I can see it. So now it's big. Now how am I going to change the axis limits? I can double click there if I want. A way to assign it is I can type in the word axis, and you can see there's the X limits and there's the Y limits. Well, let's do this. Minus 2 times pi, 2 times pi, and let's go from minus 2 to 2. So if we overshoot, I can still see it. Well, did that work? Yeah, there it is. That's looking pretty good right now. So let's now add our Taylor series, or really MacLaurin series approximations. So I want to say hold on, because I want to add more plots to this. So F plot, let's say T3. See what happens. Oh, I'm going to get a lot of that because I didn't put all those dots in there. Well, there's T3. It's okay. Let's make this a little bigger in case you're looking at this on a smaller screen. Let's make it red maybe too. So you can see it's there, and it's not a bad approximation around 0. Well, we expanded it about 0. It should be pretty good there, and it is. So that's only a third order polynomial, and you can see that basically within about plus or minus 1, it's really not too bad. Well, number 1, let's fix some stuff here. Let's say T5. Let's put that dot there and there so it isn't going to yell at me anymore. Let's add T5 to the plot, see what happens. And let's make this a little bigger. Oh, that's not a great color, is it? Okay, maybe that'll help. So you can see the blue is the exact, the red is the third order approximation, and the magenta, I guess it's called, looks like pink, is the fifth order approximation. And now we're pretty good up to about the peak here, so pi over 2, I think. Well, let's just keep going. If a little bit's good, more must be better. And I'm going to go ahead and put those dots in here again. And let's add T7. And there's another one. I'm going to make that a little bigger. Just let it stay purple, I guess. Okay, and now you can see it's good all the way out to there. Well, let's just skip the next step. Let's go ahead and add, whoops, T11. And you can see as the order gets bigger and bigger, the approximation gets better and better. So right there, that's green. Let me oops, let me get rid of that. Delete data tip. Ugh, terrible color. Let's just leave it. So you can see when I get to 11th order, I'm good way past plus and minus pi. Well, this is a periodic function, isn't it? If I'm good from minus pi to plus pi, that is, the approximation is accurate from minus pi to plus pi, that's all I need. If I go to the next cycle, I can just shift the result. So it works just fine. Once you've got an 11th order approximation here, you're really in pretty good shape. So you can see the idea here is that as the order of the approximation gets higher and higher, the approximation gets better and better. So what would happen if we did this same thing, but now expanded it about pi rather than about 0? Well, let's try it. So let's do a little bit of housekeeping here. I'm going to close that. I'm going to clear memory and clear the command window. Now, let's type in sims xy again. Y equals sine x. And let's do this again. Let's say T11 equals, spell it right, Taylor, y, comma, x, comma, pi, and order, again, 12, so I can get that 11th power term in there. Now this is going to be big, probably too big from this little window here on the screen. Ugh, there it is. All right, well, let's just do what we did before. Let's clear this now. This approximation exists only as text on the screen. So let's fix that. I'm going to go through here and I'm just going to copy the whole thing all the way out. Okay, so copy that. Paste it in there. And so it doesn't yell at me about doing vector multiplication. I got to put those dots in there. Okay, now we have it. I can calculate with this now. See, I can evaluate it however I want. I probably should have called that T11. Let's do that. Watch what I can do over here. I can rename that. So if I say T of 1, it isn't going to work because it doesn't know what T of 1 is. I say T11. There it is. Okay, now let's make T9. Now the thing in the command history says T equals, not T11 equals, so I'll call that back up and I'll fix this here. Call that T9. And I'm going to get rid of this term right there, that real long nasty one. So I've got T9 now, up to 9th power. And we like that so much, let's make it T7. And T5. And T3. Well, we've got them all in workspace now. Let's plot them all. Let's make T exact as well. I got rid of that. Okay, so F plot. Okay, as before, let's pull up that axis command from last time. That worked out pretty well. And as before, let me make this bigger, and I'll make our exact function real easy to see here. Okay, now I expanded this about pi rather than 0, so it ought to be pretty good right in there. And as I go back here, the errors should get large. So let's see how this works. Let's say hold on, because I'm going to add traces to it. Let's just add T3. Okay, let's make this, again, make this big. By the way, you can see what I did here. I clicked on that, and it actually told, if you click on the curve at a point, it'll actually tell you what the value is, and that's called a data tip. I didn't want that, so I have to delete it. So as we did before, let's make that red and 1. Okay, so there's the third order approximation, and you can see that in the near pi, it's really pretty good, even though it's just a third order polynomial. Well, T5, let's just keep going here. What you're going to see is the same behavior we saw before. That one's going to be hard to see unless you're looking on a large high-resolution screen. That might be tough to see. So make it purple there, magenta. And again, you see the exact same behavior now, just shifted over a little bit. And so as we're near pi, the approximation is really quite good. And the farther away you get from pi, the worse the approximation is. And this is very typical of Taylor series or MacLaurin series. And it's surprising how low an order you can have and still get a good approximation near the point about which you're expanding. So that's how to handle this in MATLAB. I hope this helps, and we'll talk to you next time.